Hello, and welcome back to Part 6 of the 2020 College Football Season Network Profile Summary. Once again, I am Major Andrew Dietz, and we will be using graph theory to explore the trends and analysis of the 126 teams in the FBS division of college football. The network before you represents every team as a vertex of graph age and the games played between them as the edges. Here we see the network as it has grown through the first 13 weeks of the season. At this point, the regular season is almost complete, and we have seen several ways that we can compare teams with isomorphisms and connectivity. We have also used trees and bridges to study the impact of the frequent cancellations. In this segment, we will look at the two concepts of planarity and vertex coloring. Planarity, in the context of this network profile, is when an induced subgraph of teams and their associated games can be displayed on a two-dimensional plane without edge crossings, such as shown in this example here from the Chartrand and Zhang text. Note, sometimes we may have to rearrange a subgraph to find a visualization where no edges cross. Testing this process on a large scale for the entire CFB graph would be impossibly difficult by hand. But by Kuratowski's theorem, we know that a graph G is planar if and only if G does not contain a subdivision of the complete graphs K5 or K33 as a subgraph. Remember, when a subdivision of K5 or K33 is contained in a graph, there can be intermediate vertices along the virtual edges between the primary vertices of the K5 or K33 contained graph. Using automation, we can test the entire graph for these contained subgraphs using the NetworkX command function checkPlanarity, which will either confirm if the graph is planar or provide an example of a contained K5 or K33 subgraph. For the CFB network, we quickly find this K5 example graph, which shows that Texas Tech, Oklahoma State, Texas, West Virginia, and TCU have all played each other by this point in the season, and that the CFB network cannot be planar. If we repeat this algorithm over the historical graphs of the CFB network season so far, we learn that this graph has not been planar since week 6 when a K33 bipartite graph was contained within a subgraph of 16 different teams. One creative way of visualizing the network of college football was created by an internet content producer who goes by N. Bingham, who assigns geographical territory to each CFB team, then lets teams virtually conquer each other's territory as the season progresses. In his two-dimensional map, he wants to color each region with a unique team color/logo pairing. This results in 126 different colorings for one map. Since this is a planar representation, we could apply the four-color theorem to the map to redraw the same regions with only four colors, where no two adjacent regions are the same color. However, since we already showed that the CFB network is not planar, we know that Kuratowski's theorem does not apply. If we wanted to use a program like NetworkX to recolor every vertex on the CFB graph using the minimal number of colors, such that no two adjacent vertices have the same coloring, we would start by determining the upper and lower bounds on the number of colors needed. And in a worst case, where each vertex has its own color, we have an upper bound of 126 colors used. And since we have already shown that multiple cycles of odd length exist, we can establish a lower bound of at least 3 colors. Using an automated greedy coloring algorithm, we discover that the chromatic number for this CFB graph is 5, and that this graph requires 5 different colors to accomplish our coloring goal, even though 125 of the 126 vertices can be colored with only 4 colors.